Hi, I'm Mukul Singh and I'll be presenting our paper on learning conditional formatting rules by example. Let's start with understanding what conditional formatting means. Conditional formatting, abbreviated as CF, is a popular feature in spreadsheet environments that allow users to format cells based on data-dependent conditions. The example here shows two CF rules added on a temperature information table. The first rule formats cells less than 30 in green, while the second one formats values greater than 50 in red. Conditional formatting is a powerful feature improving the presentation and visualization of data in spreadsheet. Despite being a powerful feature, there are challenges associated with authoring CF rules. Many users are unaware of this feature and end up manually formatting their spreadsheets. Even for users who know about CF, basic rule authoring often requires a deep understanding of the syntax and logic behind the formula language. The video on this slide shows the steps needed to add a simple formatting rule that formats IDs starting with RW and not ending with T. We see that the user has to navigate multiple menus and enter a complicated formula to achieve this formatting task. The formula is also shown at the bottom of the slide. Further complicating things is the limitations in the UI which lack rule validation, allowing the user to even add incorrect rules and leave the users wondering what went wrong in the rule they just added. When users cannot add their desired conditional formatting rules themselves, they reach out on help forums about their struggles. Conditional formatting is one of the most popular tags on the Microsoft Tech community for Excel. It has over 10,000 posts about conditional formatting in 2022 alone. This further reinforces users' struggle with authoring conditional formatting rules. Since adding rules is difficult for the user, we can instead switch to programming by examples. Programming by example aims to simplify complex tasks via few examples which are often easier to provide compared to a full specification for the users. The video on this slide shows how PBE could have aided the user in adding the CF rule we saw them struggling with earlier. The user simply formats one cell and then Cornet automatically learns the CF rule for the user, which he can just apply with a single click. The rule is also automatically added to the spreadsheet, saving the user the effort to navigate all the complex menus and add the complex formula himself. Now let's try to understand how Cornet works on a high level. Consider the order ID column shown. The user wants to format this column such that only cells starting with GW and not ending with T should be formatted. The user gives one example for this task and Cornet tries to learn the rule. Cornet first generates predicates for all the cells in the column. These predicates encode properties of the cells that are used to construct the CF rule. For the highlighted cell, the predicates generated are shown on the slide. The predicates are converted to Boolean features over the column based on if they are true or not for that particular cell. Using these features, Cornet first hypothesizes about the output space by generating an intermediate output formatting using semi-supervised clustering over the features. These intermediate outputs are used as labels to learn candidate formatting rules over the features. Cornet uses an iterative tree learner to generate these candidates. The generated candidates are then run using a neural ranker which uses information from both the rule and the table to score the candidates. The top ranked candidate is suggested as the learned conditional formatting rule. In this case, we see that this rule does the desired formatting for the user. We pause here, summarizing the overview of the approach. Next, we dive into each of these components in more detail. Let's start with predicate generation. Cornet uses cell properties, which are encoded as predicates, to reason about the relationship between cells which are formatted and which are not formatted. These are eventually used to construct the conditional formatting rule. Predicates are simply Boolean valued functions that take a cell C with optional arguments and return true if the property that they describe holds for the cell. For example, text equals is a predicate that takes one additional argument, which is the value v, against which it checks equality. It holds true for all cells that have value v. For each predicate, we need to generate these constant values for additional arguments. We generate these heuristically. For example, for the predicates shown in the slides, we generate the tokens by splitting the cell value into tokens based on delimiters, non-alphanumeric characters, and case changes. Having generated predicates for the entire column, an interesting thing to note here is that the space of all possible rules that can be constructed with these predicates is 2 to the power of 2 to the power of the number of predicates. This is basically the number of distinct truth tables possible with p Boolean variables. The space of all possible formatting, on the other hand, is only 2 to the power of number of cells in the column, as each cell can be either formatted or not formatted by a rule. Cornet takes advantage of this size difference in search spaces, which shows that the formatting search space is much smaller than the rule search space. Hence, Cornet first generates labels for the column, which might be potentially noisy. To do this, Cornet uses an additional user signal in the form of soft negative examples. This is based on the assumption that users annotate data top-down and anything not annotated between labeled examples is intentionally left blank. To not bias the model too much towards this, we keep these examples as soft. We perform iterative clustering over positive, negative, and unassigned clusters, which are initialized with cells of their types and iteratively updated till the clusters stabilize. For example, in the example shown in the slide, the first 3 cells are soft negative example, and the 4th cell is a positive example given by the user. These cells are then clustered, and finally we get the noisy formatting predictions for the column. The next step for Cornet is to generate candidate rules. We address 3 challenges with our enumeration. First, we want the candidate rule set to be diverse. Second, we want these to be simple. And finally, we have to cope with noisy labels generated in our clustering. For this, Cornet uses predicate-based Boolean features to learn a decision tree over the predicted output formatting from the semi-supervised clustering. The resulting tree can then be linearized into a CF rule. This generated rule is added to a set of candidates, and the feature used to construct this rule is dropped from the training set for future iterations. This process is repeated iteratively until the accuracy drops below a threshold. This gives Cornet a candidate set of rules. Next, we need to rank these candidate rules. For ranking, Cornet uses a neural ranker that uses information from both the rule and the input column to rank candidates. Features from the rule are manually constructed based on heuristics. For example, the number of cells the rule colors, the predicate used, the constants used, etc. The input column is fed into a BERT encoder, which uses cross-attention over formatted and unformatted cells to learn linear features. The features from the rule and the input column are then concatenated and fed into a linear layer, which transforms them into a single score that is then used to rank the rules. We will now look at how we evaluated Cornet and see how it does in practice. We use a corpus of 1.8 million public Excel workbooks scraped from the web. Out of these, we find 236,000 workbooks to have at least one CF rule in them. This eventually gave us 410,000 CF rules. After deduplicating and splitting into train and eval tasks, we got 80,000 train tasks and 25,000 eval tasks. The train tasks are used to train any baselines and the neural ranker in Cornet. The evaluation tasks are used for evaluation. We also release the evaluation tasks publicly to further research in this direction. The link to the benchmarks is on the slide. We perform extensive evaluation in our paper with 9 baselines, both symbolic and neural, adapted to the task of conditional formatting. Here we discuss 2 highlights, the best symbolic and the best neural system from the baselines. Popper was the best symbolic system, which is a state-of-the-art ILP system with excellent results on multiple programming by example tasks. Tuta was the best neural system, which is a tree-based transformer model that has been pre-trained and fine-tuned for the task of cell type classification, which is very close to the conditional formatting task. We now see how Cornet does in practice. The slide shows the top 1 execution match accuracy for Cornet along with Popper and Tuta, which are the best baselines in the symbolic and neural category respectively. We see the performance along with an increasing number of examples provided. We see that Cornet is clearly better across the board compared to other systems. A similar trend is observed in top 3 and top 5 results. Next, we try to analyze how the number of inputs affect rules for different data types. We see that text rules can be learned accurately with just 2 examples, while numeric and date time rules often require much more examples to generalize. This is because of the larger search space required to learn numeric and date time rules. We find that text-based rules are more frequent in the corpus. Let's also talk a bit about the neural ranker behind Cornet. We see that Cornet's ranker is better than both the purely neural and purely symbolic counterparts. One interesting thing to note here is that the symbolic ranker is not too far off the performance and can be a good candidate in resource-constrained domains where a full neural model cannot be deployed. We also want to highlight that Cornet is aimed to help both novice and experienced users. As highlighted earlier, conditional formatting has poor discoverability, and Cornet can help new users to learn about this feature. The slide shows some examples of columns found in public spreadsheets where the users have manually formatted the sheet, but a simple rule could have been learned by Cornet. The slide shows the column along with the rule that Cornet could have learned. We find that 80% of these cases could have been solved by Cornet. In a sample of 100k columns, with at least 5 cells, 3 of which were formatted manually, we find that in close to 93% of these columns, Cornet was able to learn the rule that generated the target formatting. 80% of these learned rules had 3 or fewer predicates. We find that even experienced users who know about the conditional formatting feature and can successfully add correct rules often write unnecessarily wrong rules, which are harder to maintain and generalize to new data. Cornet can learn a simple rule in these cases. The slide shows some example where the user-written rule can be simplified by a rule learned by Cornet with a few examples. At its core, Cornet is simply learning a conditional program using few examples. This approach is applicable but not limited to conditional formatting and can also be extended to other related domains. In our paper, we also explore applying Cornet to related domains like filter rule generation and conditional formula generation. Results for both problems are shown on the slide. We found that filtering cases resulted in a higher performance than learning formula conditionals. We believe that this is the result of our grammar, which is well aligned with predicates available in the filtering interface and those found in the filter function. In contrast, conditional formulas may use different functions as well as use numeric conditions more often. Extending Cornet's grammar with such predicates could help mitigate the performance difference. These were the highlights of some of the experiments done in this work. The paper contains many more experiments and detailed analysis. Thank you for watching this presentation.